computer. All right, so we'll do that. All right, so this week right here, remember, we're going to be finishing up our Module 9. Our Module 9 homework is due on Top Hat on Monday by midnight. We're going to start Module 10 next week. Module 10 is radicals. So it's a completely different kind of chemistry than what we've been doing now. And it has some really unique nomenclature and regioselectivity. We introduced that a little bit in the reactions of alkenes, where we saw that when we added a peroxide to our HBr, we actually got anti-Markovnikov addition because we formed a radical. And so we're going to talk about more about those radicals and how we can have some fun with them. Okay, so that'll bring us in through up to the week of Thanksgiving. I need to double check on whether we just have one class that week or two classes that week. I currently have scheduled 2 classes that week. So we'll see what happens there. We will probably start Module 11 at the end of next week, by the way, just giving you a heads up. Okay, so are there any questions about this week or what we're going to be doing? We're going to finish up Chapter 9 with mass spec, and then we have an activity on NMR. I figured I better do an activity on NMR because I need you to figure out how to pick out unique hydrogens, then be able to count the number of hydrogens that are adjacent to something and show splitting, and then get a relative idea of shift up and down field. So I thought I'd do a little activity on that and help you work through it together and kind of visualize it and get used to the concept. So that's what I want to do with the activity here in about 20 minutes. Okay. So without further ado, go ahead. My chat's open. I can see it right here. So everything's good there. I'm about to share my screen. So I'll have my video up here on this side over here. So if you want to ask something there, you can. All right, so here we go. We got our slides up. So just like in the other 2 modules, I'm drawing your attention to the 4 things we must consider in our mass spectrometry. Mass spectrometry is actually a cool technique because what it does is instead of actually detecting a radiation, what we do is we detect the mass of the particular ion. And then from that mass, we get a relative idea of which elements are present, how many hydrogens and carbons and oxygens, and so that we can use this to help us elucidate the compound. So let's say you made a mixture of compounds. Well, one of the tests you do is you could run it through a mass spectrometer, and it says one of them has a molecular weight of 155. The other one has a molecular weight of 270. Well, now you know those are 2 very different molecules. And then in addition to that, we can look at the way these molecules break up in the mass spectrometer. And that gives us certain ideas about what the fragment pattern is. The fragment pattern tells us about where the weakest bonds are. So when you have big fragments coming off, that means those fragments were attached to weak bonds. And so you can start building up your structure based on the different fragments you have. So the whole concept happens because we take a molecule and then we ionize it, and then we push it through electric and magnetic fields to help separate them by mass. And once we separate them by mass, we get what we call the mass spectrum, okay? And in this mass spectra we need to consider 4 important things, okay? We need to look for the molecular ion peak, okay? The molecular ion peak is typically the highest molecular peaks we see, and that tells you the molecular weight of the compound you're looking at. So that's the molecular ion peak. So it's the furthest to the right. In mass spectra, we go from intensity on the y-axis to starting from 0 on the left and going up in mass toward the right. So we're looking for the highest to the right peak. Obviously, my allergy medicine has not fully kicked in. Okay. The second thing we look for is what we call the base peak. The base peak is the tallest peak. Rarely is the molecular ion peak the tallest peak because it starts to break apart and have fragments. So we usually have some peak that's other than the molecular ion peak be our base peak. And that base peak tends to be the most stable fragment of that bigger molecule, okay? And there's one trick to that, and I'll tell you about that as well. The next thing we have is what we call relative abundance. And so if the base peak is what we relatively call 100%, all the other peaks are some percentage of that peak. So let's say your molecular ion peak is 50% of that base peak, and then all the other peaks would add up to be other things. So let's say you have another fragment, a really common fragment, that is at 50%. You'll know that those two big fragments, the base ion fragment and the relative abundance, the highest relative abundance fragment, are the two that you need to start looking for that fragmentation pattern. And that's the last thing we look for, fragmentation pattern. There's a couple of different things we can see from fragmentation pattern that tell us things about the molecule. For example, if you have a mass spectra and you have a molecular ion peak, and then it goes and has a fragment that's 13 grams per mole loss, 12 grams per mole loss, 12 grams per mole loss, 12 grams per mole loss. Well, that's what we consider a long chain hydrocarbon, because it's losing a methyl group, a CH2, a CH2, a CH2, a CH2. That's a unique fragmentation pattern to a long chain hydrocarbon. And so we can tell a lot of different things from mass spectrum. We can tell whether there's a lot of branching or whether there's a long chain. And sometimes we can even tell when there's a ring. Okay, so let's start looking at some of these factors. So this is what a mass spectrum looks like right here. And like I said, our relative intensity is on the y-axis here. It's relative because the amount of actual particles you get depends on how much you inject into the machine. So it's always a relative amount. And then we have the highest peak we see is the molecular ion peak. So this is the mass of the analyte we're looking for. In this case, we're looking at ethanol. And so that would be this right here. And so we have 1, 2 carbons plus an oxygen, plus 1, 2, 3 hydrogens, 4 hydrogens, 5 hydrogens, 6 hydrogens, which should give us a mass of 46. So we actually see that molecular ion peak. Notice there's one at 45 here. That happens really commonly in alcohols because we lose a hydrogen. That's a very easy thing to lose, and therefore we have that as a significant peak. But it also tells us we have an alcohol because it's a loss of 1 hydrogen. Now, the next thing we look for is number 2, our base peak. Our base peak is what we call our relative 100% right here. And that should be a very large fragment. In this case, it is 32 grams per mole in size. Okay, so 32 grams per mole is probably an oxygen and a carbon. 2 carbons together is 24. So the fragment here is going to be carbon-carbon, which is 24, 25, 26, 27, 28, 29. So that should be another major fragment. And we see it right here as 28. So by taking the molecule and breaking it apart, we can see which different fragments leave. The other thing we can tell is if this is 32 and this is 46, 32 minus 46 means we lost exactly 14 atomic mass units, okay? So if we lost 14 atomic mass units, what does that equate to? That's a CH2. So that's a common fragment we would see lost. So looking at the difference between fragments and looking at the major base peak gives us information about the compound. All right, so when we analyze things, the first thing we do is we identify that molecular ion peak, because that tells us the basic place where we can start finding our empirical formula. Now, based on that mass, we consider the possible empirical formulas based on that. So let's say you had an atomic mass of 100. Well, we can figure out that it would have, you know, if carbon has 12 grams per mole, that's the mass of carbon. We know we can't have 10 carbons in here. So we know we have to start back somewhere else, like let's start at 8 or 7 carbons. So that begins to give us that possible molecular formula, okay? The next thing we do is we identify the major peaks. Now, major peaks are something that are very strong, and they tend to be, there's always going to be some minor peaks there, but you're looking for the strong, I would say you would start at anything above 33% on the relative intensity and start looking at that. And then we calculate the mass loss between the molecular ion peak and those fragments. And with that mass loss, we can start building little blocks. If you lose 14, that's a CH2. If you lose 15, that's a CH3. If you lose 17, that's an OH. So you can look for common masses right here. So literally we have to look at the just the mass of the different types of atoms and what they would normally have hooked onto them. Okay, so let's try that and look for some other, let's kind of do that analysis on this peak here. So this is kind of a complicated one, but it's really going to show us all these different techniques. So the first thing we do is look for the molecular ion peak. And so that's going to be this highest one. Notice there are some little, you know, kind of smaller artifacts in the system, but the large peak here, you know, it's above 33%. This is our molecular ion peak. And our molecular ion peak here is at 122. So that tells us, it gives us our idea that our molecular ion can have a C8H10O, okay? And that's the molecular ion peak we were looking for because we knew we started with this material here. Now, how do we get to that? Well, we have 6 carbons here, 7 carbons, 8 carbons. So that's where the 8 comes from. We have 5 hydrogens here, 6 hydrogens, 7 hydrogens, 8 hydrogens, 9 hydrogens, and 10 hydrogens. And then of course our oxygen is our last one. So our empirical formula is the same as the structure drawn. So that's a great start. Okay. So then the first thing we look for is we start looking at the first ion and the difference in mass between the first ion and the first fragment and the molecular ion peak. And so if we look at that, we go from 122 to something like, looks like 116, which is a loss of 15. Loss of 15 is really classically a CH3. You have 12 for the carbon and then 3 more for each for the hydrogens. So that's a total of 15. And so at that point, we see that we've lost 1 carbon and 3 hydrogens in our molecular formula. Our next fragment turns out to be right here at 79. 79 is this little compound here. It's basically, we started to clip benzene off and it has an extra hydrogen on it. And it's got a charge right here. And this is really common to happen. We wouldn't see this in the lab, but we definitely see this in the mass spec. And so, but that's a loss of just an oxygen and a carbon. So that's going to be a total loss of 28 right here of that oxygen and the carbon. But then there's another one where we can actually lose the oxygen, the carbon, and 2 hydrogens. And that gives us a peak at 77. And 77 is the molecular ion peak for just benzene itself. Okay. And then if we see a loss of the entire benzene ring by itself, we end up getting the remaining fragment here. So we're looking at those different losses, and from those different losses, we can identify each of the peaks we see in the mass spectrum. Okay, so the other thing we look for is fragmentation, and that fragmentation will always happen in the system because it's an ionized system and they're in vacuum. And so what they're trying to do is break apart to form the more stable part more stable ions and neutral compounds or radicals. And so these are constantly going to rearrange and break apart into smaller bits. And then we can see those different little bits in that fragmentation. But we we don't lose any of the fragments. The fragments are just analyzed and break down even more. Okay, so there's two common fragmentation patterns I want to talk to you about. The first common fragmentation process is when we have hydrogens on a carbon next to a carbonyl. And those hydrogens on those alpha carbons can help with a rearrangement, a radical-based rearrangement, to where we break between the carbon with the carbonyl and the carbon next to it. So we're breaking that alpha carbon. So if we have a carbonyl here, the one carbon next to it's our alpha carbon, and it's what we call alpha cleavage of carbonyl compounds. Now, this is really cool because if you have something like a methyl ketone on the end of a reaction, that comes off as a very strong peak. And so you can identify it really easily. So that's one fragmentation that happens a lot. The second kind of fragmentation that happens a lot is when you have a long chain hydrocarbon next to a carbonyl or a carboxylic acid. And that's called the McLafferty rearrangement. And instead of cleaving at the alpha carbon, we have to have a beta carbon and a gamma carbon. And what happens is the hydrogen from the gamma carbon is transferred to the carbonyl, and it cleaves in between the alpha and the beta carbon, giving us a different fragment than we got from the alpha cleavage. Okay, so these are two very common things, and both of them happen in the presence of carbonyl compounds. And so we'll see both the alpha cleavage right here and this alpha beta cleavage in the McLafferty rearrangement. And it all happens because we get to form this transition, this 6-member transition state, and then just move individual electrons around because we already have this ionized radical, this ionized compound, and it gives an additional radical. And then these can be seen by the mass spectrum, spectrometer, sorry. Okay, now that's just for, it'll give you things like, you know, carbon 12 or nitrogen 14. Okay, so when we have those kinds of spectrum, it's just giving you atomic mass units. It's not giving you any fine detail. However, there's also another one we call high resolution mass spectrometry. And in high resolution mass spectrometry, we actually can measure the individual isotopes of the elements to 4 decimal places. Now, this is really important because if you can go down to 4 decimal places, that means at the end of that calculation, once you get the answer there, you know exactly which elements you have and how many you have, because you've analyzed it all the way down to 4 decimal places. And all the different isotopes have different masses, and you can back calculate the exact molecular formula. Okay, so in the case of something where you could say, well, my mass is exactly 256.3758. Okay, I just happen to have a book here. I can look that up. So if you had your high resolution mass spectrometer and it came up and it said that you had that exact mass, 156, oh, let's go back to 246.2183. That means we have an exact molecular formula of C12, H28, N3O2. And we were able to back calculate that because we had all 4 decimal places here, and we can compare and contrast all the different 4 decimal places for each of the elements and get an exact molecular formula. So when we have the unit or the atomic, gram per mole unit resolution, we have to look at fragmentation and stuff like that. When we have that 4 places after the decimal, we get an exact molecular formula every single time. All right, so that's our introduction to mass spectrometry. It's another tool we use to help us identify the organic molecules that we synthesize in the lab every single day. Questions on mass spec? There are a couple questions about this in the homework, so you'll need to answer those. Okay, well, now it's about time to switch over to the activity. Okay, so let me pull up the activity and give you a few instructions. Activity. Okay, I gave one example for this activity, and so let me minus and share my screen. I want to explain the activity and kind of help you get to the idea of what we want. Okay, so here is the activity that we have. This is our, there we go. All right, so the instructions are to determine the number of unique hydrogens and label them A, B, and C. Okay, so in this first example, notice I've labeled the unique hydrogens on the top and the unique carbons on the bottom. And because this is a symmetrical molecule, these two types of hydrogens are the same, and these two types of hydrogens are the same, okay? So in here, you'll probably not have any shared hydrogens. You're not gonna have any shared hydrogens, but you will have shared hydrogens in that last example. So it'll be like AA, B, B, C, or something like that, okay? So that's the first thing you do, and we label it like this. The second thing is you want to determine the multiplicity, that n+1, of each set of hydrogen atoms. So A is going to have one number to it, and B is going to have another number to it. And so what I did to help you identify what the multiplicity is here is I showed you the equation 1 plus n, but then I told you where n comes from. So in this case, A right here has 3 hydrogens on it, but it has 1 signal. So that's where the 1 comes from. But then the N is the number of hydrogens within 3 bonds. And so if we go there, we only have 2 hydrogens on the B hydrogens. So that's where the 2 comes from. And I'm identifying it with a B to show those hydrogens come from the B hydrogens. And so that equals to a total of 3 peaks. So that means our multiplicity is 3, or give us a triplet, okay? So that's what I'm looking for in an answer. And B, we have the 1 hydrogen for the B hydrogens, but the B is next to the A, and there are 3 hydrogens on A. So I have 3 A hydrogens is equal to a total of 4. So we're going to get a quartet on that B peak. Then I say, at the last thing, rank in order from highest to lowest ppm number where you think the hydrogens would be found on the thing. So in the shift here, what's going to be higher up? You know, things that are alkenes, things that are next to carbonyls, things that are next to halogens are going to be higher numbers further downfield. Things that are most like methane are going to be further upfield, closer to 0. So in this case here, because the B hydrogens are next to this oxygen, we feel those are going to be higher than the A hydrogens. So you just kind of rank them in relative order. Now, if they're too close to call, you know, they're like 3 or 4 of them look, they'd be about the same. It's easy to tell this one and that one, but these might be all in the same group. You can put them all together, saying, you know, just like C, D, and E are all about the same, and just put commas there. Now let's do the carbons here. So I labeled them in capitals here on the bottom halves here. So we have A carbon and a B carbon and a B carbon. And so that would give us that. And then we rank these in order too. And again, the B is next to this oxygen. That's an electronegative atom. So it's going to be furthest downfield. So we're going to label it first B, and then the second one A. Now, notice that when we go to this one right here, you're going to have A, B, C, D, E for your hydrogens, but you're going to have A, B, C, D, E, F for your carbons, because your carbonyl carbon counts as a carbon, and it's going to be way shifted up downfield, but it doesn't have any hydrogens on it. So that's why I wanted you to label them differently for hydrogens and for the carbons. Okay. And so what I want you to do is go ahead and break out into some breakout rooms and go ahead and do this exact thing for all three of these compounds. When you're done, go ahead, take a picture of it and upload it to Canvas by midnight tonight. Okay. So let me stop sharing my screen and break you out into, let's say, 4 breakout rooms. Okay. Does anyone have any questions about the activity? Okay. Really quiet day for a Friday. All right, so what I'm going to do is I'm going to break you out into your breakout rooms and then let you go ahead and try this out. Talk together. You can use your book, but try to figure out how this is working so you get it straight in your head. All right, 4 breakout rooms assigned automatically. I'll open the rooms now.